Good morning, Michael. I see in this glorious morning we are looking at points to intervals, but you have an extra word here. We did look at why we do this, but from linears, we're now going to cubics. So what's your idea?
Well, my idea was to review a bit about the linear part to remember where these basis functions came from. The idea was we want to look at the function values at 0 and 1 and say, well, we just multiply those by the basis functions and get what we want. And the basis functions, basically, each one of them had two conditions. This first guy, b0, we want to take the value 1 at x equal to 0, and then at x equal to 1, it should take the value 0. That way, we can use it to match the value of the function at x equal to 0. And then this other basis function, it's the other way around, takes the value 1 at x equal to 1, and the value is 0. So these are the nice basis functions. And basically, you see each of the functions has two conditions. It has to take a certain value at x equals 0 and another value at x equals 1.
And you know what I like about this picture, just to remind ourselves that intuitively would make sense, is if we wanted to evaluate at x equal to a half, then b0 would be equal to a half, and b1 would be also equal to a half. So it would be a weighted average, in this case equally weighted between 0 and 1, halfway between. So the use of the basis functions this way is great. It's very intuitive.
Very intuitive.
Now, if we want to go to cubics, what are we doing differently?
Well, first of all, it's not going to be linear. It'll have to be some sort of cubic. Okay, so let's write down a cubic. I'll write down just one of them.
Yeah, so let's look at b0.
b0, okay, so I'll use my pink for that. It's going to be some form a plus bx plus cx squared plus dx cubed.
Are you going to leave this up? It might be a little...
Let's take that out because it's a little confusing. And you know what? Because it's a cubic, it's not going to be, b0 will not be a straight line. It's going to be a cubic. And what do we want it to do? Well, we want it to...
the four conditions. We could write down the conditions for
I'm going to draw a
B0.
picture of the conditions. Okay, of course, we want it to take the value 1 at x equals 0. We want to take the value 0 at x equal 1. But then we want to know that the derivatives won't mess things up. So I better want a derivative to be 0 here and a derivative here. So those are my four conditions.
So they're going to, whatever this cubic is doing, it's going to be locally flat here and here.
Yeah, so you sort of, cubics are little curvy things. Go and flatten out here. Flat there, flat there.
But normally, that's the function, but the point is that is the derivative going to be 0 there? Yes, it is going to be 0 because we don't want any derivative conditions to mess up b0.
So let's write down what our conditions are. We want b0 at 0 should equal 1. b0 at 1 should equal what, Matt?
0.
And then the derivative, b0 prime at 0 should equal what?
0.
Because we want it to be flat. Right? And the derivative at 1?
Also flat.
Okay.
Oh, great. So this should be easy to write down now.
So if I look at that, if I plug in x equal to 0, what do I get?
I get a equal 1.
Isn't that great? Now we know what a is. A is 1. Yay!
Yeah.
Okay. Plug in equal to x equal 1, what do I get?
Well, 1 plus b plus c plus d equals to 0.
Yeah, because we know a is 1, so this is 1 plus b plus c plus d is equal to 0.
And now we need the derivative. So a doesn't matter.
Tell me the derivative.
It's b plus 2cx plus 3dx squared. At 0, these are going to vanish. And so we get b equals to 0.
Which is nice because I can get rid of this now.
And I put it equal to 0 there. Yeah.
It equals 0.
Oh, it equals 0 there. Okay, and the last one, b prime at 1. So it's going to be The derivative is here, so substitute x equals 1.
Okay, b, of course, is 0, so I don't have to write that down. Get a 2c plus 3d.
And that's equal to 0.
Okay, so I've got two equations in two unknowns, c and d. Some of us can do this in our head. My son likes to do this in his head. He said, well, obviously, these guys got to cancel, so one of these got to be like a 3 and the other one is a 2, and then you have to put the signs right so they cancel. And here, you know, they got to add up to -1.
Right.
That's how my son would do it. Some of us have a more routine ways of doing this. Another way you could look at this is say this is 2 times c plus d is equal to 0. And here you see that c plus d is equal to -1. So you get 2 times -1 plus d is equal to 0. That tells me d is equal to 2. This tells me c is equal to -3.
Okay, there's our cubic. Let's write it down and then we'll draw it.
So here we go. B0 is equal to
1
1
plus minus 3
x squared
plus 2x cubed. There it is. What does it look like? Well, it's pretty much what you've drawn. Maybe it...
One thing we'll notice is, okay, it's got an x cubed, so as x gets big, like a million, this term is going to be huge and positive. So this function is going to go whoop like that.
Yep.
If x is negative, whoop like that. Okay?
Yep.
So you notice it crosses the line here. You notice you have a double root here.
Oh, wait. I forgot double root. Where did that come from?
Oh, where did that come from? So you know that polynomials, usually you can factor as like an x minus x naught times an x minus x1, x minus x2, and so on. This guy has an x minus 1 in it, but if you only have one of it, it's going to go kind of straight through. So a double root is like the bottom of a parabola. It's like an x squared type term.
And it's located at 1, so then you got the x minus 1.
So I'm going to have an x minus 1 here.
Squared.
And then I notice that I have a 2x cubed. This has to multiply by the x squared that comes out here. So I better have a 2x here. And then when I multiply this out, I get a plus 1. I want to get a plus 1 here, so I can factor this in my head.
But tricky, because you started matching powers, x cubed and x to the power 0, and that worked. But you also used the fact that this has a double root.
I did.
And I think it's key to do that. Otherwise, it gets kind of a messy operation. But you know, in a sense, when students are learning factorization, they learn a procedure to divide things and stuff, but they don't learn the geometry. And since cubics is about as far as we go with trying to do things on the blackboard, this is a really important result.
It's an important result, and it's actually really quite nice. It also sort of tells us how we would find B1. B1, we could do a similar type of thing, except we put a 1 here and a 0 there. You could solve it all, or you could say, you know what? I know what B1 has got to look like. B1, it has to go through here and here, but it has to be flat here and flat here. So, okay. How does that work?
Does it have a double root at 0?
If it's going to be flat at 0, it better have a double root. So that means it's going to go up like this.
And then it's got to go down.
And you look at that and say, okay, here I've got an x cubed. So it'll be 1 of x. Matt, I'm going to wow you with my mathematical genius. But it's got to have an x squared in here. And over here,
this is at 1.
At 1, it should take the value of 1. I'm going to get...
Well, why don't you deal with it? Is it a double root there? No, it's no root there.
I think this is what it is.
Well, where did that come from?
Where did that come from? Yeah, that's a really good question, Matt.
y minus 2x cubed. You know, I think this is something that we could spend a whole video on, and we could do that. So let's just take it and then put a question mark there.
Question mark. And this can be an exercise for you to do at home.
Oh, okay. It sounds great. Wonderful.
Thank you, Matt.